Okay, I hope you have a great day so far. Let's just start today's session. In previous sessions, like last week, we talked about the power flow analysis, which was the steady state analysis of the behavior and response of our power system. We talk about the general uh, methods and basically theory and equations that exist for power flow analysis. And in Thursday, we talked about the effect of IBRs on those general methods and equation and how we could modify the Jacobian matrix into uh, suitable uh, power flow analysis for power systems uh, dominated by inverter-based resources. Now, this week, we are going to cover the transient stability and the transient analysis. So previous week was steady state. Now we are going to go toward transient. Okay. First of all, let's talk about we want to talk about the transient stability. Let's talk about what is a stability, what we could define as a stability in power system precisely. Okay. When we talk about the stability, the definition of the stability is basically the ability of the power system, or generally in any other system is gonna be the same definition, uh, to return to the steady state after a disturbance. The disturbance could be a minor, like a small load change, okay? Or it could be a very kind of like large disturbance, like a fault or any type of malfunctioning in the system, okay? So the stability definition is the ability of the system to return to the steady state after any type of disturbance. Are we good so far? Now, there are one other definition that sometimes it gets confused with the stability criteria and the stability definition, and it's the system response. Okay, we already talked about the definition of the stability, but what is the system response? I wanted to clear that so we won't confuse the two topics with each other when we move toward the transient stability analysis. Now, the response of a system or system response is how the system behave, okay, when it's disturbed from the equilibrium of its dynamic. What that means? That means we have a system, it works in a steady state, okay, meaning it's in equilibrium of the current condition, okay. Now, for any reason, it could be a load change, it could be a fault, it could be like a lightning strike in our power system, okay? For any reason, there is going to be a disturbance or a variation in one of the parameters, those important parameters that we had: voltage, frequency, current, power, okay? Those four important parameters. One of them get disturbed, have a variation. Now, how system would respond to that uh, disturbance? We call it system response or system dynamic analysis. Okay, that is only covers the behavior of or the output of the system when you have a delta variation, like delta theta or delta F or delta V as an input to that system. So that's going to be system dynamic or system response. Stability, as we talked about, is not about what's going to happen after a fluctuation or a variation. It's the ability of the system to handle that variation and get back to the steady state. Makes sense? A different kind of like concept. Do not get confused between, do not misunderstood these two with each other. Okay? It is happening a lot actually. So I wanted to be emphasizing on that and clear that. Now, why actually the transient stability is important, or generally stability, why stability is important? Okay, we are talking about the system. It's important because whatever system you design or whatever system you want to use, one of the most important parameters of engineering design of that system is that that system should be reliable. Okay, so we are not gonna have like a temporarily kind of like one-time usage of the system. It's gonna stay strong, work reliably for a long period of time, especially in like a system like power system where the infrastructure are huge and very expensive. Okay, so reliability is one of the reasons that stability is critical or important in power system analysis. Okay, besides reliability, when we talk about the stability, we say, okay, the definition of stability was to the ability of the system to go back to the equilibrium or the steady state after a fluctuation or a fault or any disturbance. Okay, if the system is not able to do that, that means not only we are not reliably provide the benefits of that system, the output of the system for users, not only that, but also because the system cannot handle the disturbance, it kind of like fell into a negative loop and another disturbance would happen. Another like generator would get damaged or like seize the power injection into the system. Okay, they are gonna break the connection, the protection system, and it's kind of like getting like a cascading failure into the system. Uh, does that make sense? Now, in power system, we also we said that we also have a very critical condition in power system, and it was that frequency, the 60 hertz or 50 hertz frequency that we have. We already talked about how important it is in our system. Now, one of the one of the concept that makes the stability analysis important is that if the system is not stable, that means we cannot provide a, a stable frequency, a constant frequency, and we cannot guarantee the synchronism of all the generator in our system. So stability also one of the byproduct of having a stable system is that, okay, now the system is strong enough to manage a disturbance, meaning it could keep the synchronism between the generators. And by generators, I don't mean just rotary machine. It's all the resources. It could be inverters, it could be any kind of like resources, energy storages, all those. Okay. Now, in transient stability, in stability analysis, okay, we have three different type of analysis. One is called transient stability. These are three main. There are more analysis, but these are three main one. Okay. One is transient analysis, which is the system we are going to talk about the system ability to maintain that synchronism. Okay. So transient analysis is focusing on that synchronism part because the frequency is very important for us in power system. Okay. The next one is dynamic stability, which is basically that system response to any fluctuation. And now we wanted to see, analyze the response of the system and find out how it would affect the stability. So these are two different things. Dynamic, stability, two different things. We wanted to like see how they affect each other. Okay. Now, The third one is a steady state stability, which is how the a system would react or maintain the equilibrium point when we have a gradual change. We already talked about that in last week. That was a stability like powerful analysis. We wanted to like see what would happen if we have a gradual change like load flow or load change. Okay, these are gradual change, not sharp like short time changes. Okay, so these are the three main analyses that defines the stability of the system. Now we already covered the steady state. This week we are going to talk about the transient one. Okay. Now, in transient stability, we have some critical focuses that we have to like have in order to make sure that our analyses are comprehensive and we cover everything. Okay. Before I get to that, I put a kind of like a time scale graph of what that means because I wanted to like make sure that you understand what I mean by transient stability and steady state. The difference of steady state and transient stability and transient state, basically, when we're talking about the incident that could happen in a system. As you can see, we have an electromagnetic transient, which is a very short time. The x-axis here, the x-axis here is time. Okay, so it's 10 to the minus 7, so it's microsecond, kind of like less than a microsecond time scale. Okay, these electromagnetic transient are very fast, instantaneous kind of like disturbance, like lightning strike. This happen instantly. It's very short and very sharp kind of like disturbance. Okay, or switching or inverter, also inverter-based control system also happen to that electromagnetic transient. Electromagnetic transient are the short time transient, very short time transient. Now we have electromechanical transient, which is basically the conventional definition of the transient before inverters was introduced to the system. Okay, those electromechanical transients have a higher time scale regarding the electromagnetic transient. Okay, and it's normally like the transient stability that we talk about is mainly covers that time scale. Okay, it's like how disturbance in a rotating machine, like in a stator of the rotating machine, would affect the system. Okay, or how the governor or like a frequency control of a rotating machine would react to the load flow or any disturbance. The control system in a rotating machine are much slower than the control in an inverter-based system because it's mechanical in rotating machine. It takes more time to adjust. So that time scale is what we call a transient. Okay. Now a steady state, the changes or the gradual changes that we define for a steady state is like powerful. We talked about that in previous, okay, or a unit commitment, meaning like you probably heard about the control unit of a power system when they assign a certain amount of like power generation to each power plant. So they are sharing the load between the generators. Okay, that's like unit commitment or like these very high time scale. It happened like maybe the time scale on that is if you call it like a second, it's happened like in 1,000 seconds, which is like normally in a day. Okay, each day they would change that. Make sense? The power flow would happen like in hour scale or in like a few minutes scale. I wanted to like give you the sense of what I mean by a steady state, gradual compared to transient, compared to that ultra fast electromagnetic transient. Okay, the inverter-based resources are on microsecond scale. A steady state that we talk about is in minute or like hour scale. I wanted to like show you how different they are. Now, what are the critical focus of the transient stability? Let's go into that. One is what happens if we have a large disturbance. Large disturbance would be like a fault, like a line to ground fault, or a three-phase fault, or two-phase to the ground fault, okay, or line to line fault. There are several type of faults that happen in power system generally. Okay, so the fault is one of the large disturbance, as it would affect the voltage in a very kind of like high margin. There could be a line tripping for any kind of reason. Sometimes relays are tripping the line or like short open circuit some part of the system by mistake. That would happen. Okay, so one line gets tripped out. Or even sometimes there is like a environmental hazard. Like you've seen we are living in Oklahoma, so you've probably seen in the news those flashlight when tornado happen. They are normally is like one line is destroyed by the tornado. So we lost the line. That's a huge kind of like disturbance in the system. Or generator outage. For any kind of reason, a generator cannot provide the power that it used to provide. That is a big change. But generators are not a small part of the system. They are normally working in megawatt scale. Okay, so another parameter that we have to pay attention to is that all those disturbance that we talk about in transient stability, all of them happen in a short time frame. Why is that important? Okay, in the power system analysis, okay, in the power flow analysis, the equation that we had was P and Q based on the RMS voltages, okay, VI, VJ. Do you remember that formula? VI, VJ, time B or X, whatever, okay, that we have, if Z impedance or Y, if impedance base or admittance base, okay, times the difference of the deltas or difference of the deltas. Do you remember that? That was the formula for the power flow. So what we had was difference of the delta, reactance, and the RMS voltages. Now, I want to ask you a question. If anyone can say why, when we talk about a short time frame, meaning like a 1 millisecond or 1 microsecond faults, why we have to move on from those parameters that we had in power flow, the RMS, the impedance or reactance, and the delta changes. Why those parameters are not sufficient enough, okay? So we could use them when we talk about the short frame or short time frame disturbances. Anyone can have any idea of why is that the case? And we need to introduce a new kind of like analysis. There's no time. That's true. Let me rephrase what you said, okay? Restate. That's a good answer. I want to rephrase that to be more general, okay, and to the point. All those parameters, the RMS, the impedance, okay, all of them, they are, as your friend said, is a frequency domain uh, parameters. When you want to calculate the RMS, you calculate the RMS based on all the data you have in at least one cycle of sine or cosine, correct? Again, when you talk about the reactance or impedance in general, impedance depends on frequency. That reactance is either j omega L or 1 over j omega C. We have omega in it. So meaning we have a frequency, meaning we have to have at least one cycle of sinusoidal happened so we could have the frequency or the averaging RMS. Make sense? So if we're talking about the millisecond or microsecond values time or disturbance, on those time frame, we don't have one cycle. Okay, so we don't have frequency on that time cycle. We don't have enough data to calculate the RMS. We don't have enough data to calculate the impedance. So we can move on to frequency domain. So we have to deal with that in another way. Make sense? Are we clear on that? Any question about that? Now, yeah, go. Sorry.
Oh, so you mean because it's a small time frame, it doesn't last the whole period, so we can't rely on frequency of so
the disturbance alone, okay? The effect of the disturbance could last longer than a period. Okay, but the disturbance itself, the transient disturbance, are less than one cycle. Normal, like it's fault, it happens instantly. Lightning happens instantly. The effect may still be around, like when the fault happens, until the fault is clear. It normally takes 2 to 5 cycles. Okay, so but the fault itself is not 2 to 4. You know what I'm saying? The disturbance is not that high. The effect could go longer than a cycle. Make sense? Yeah. Did I answer your question generally?
Yeah.
Okay. Now, the third part that we need to have a new stability analysis is that the effect, the stability analysis, we are going to see that it's a nonlinear behavior. Okay. Hold on to that thought. I'm going to show you in the equation what I mean by nonlinear behavior when we talk about the transient stability. Okay. And basically, it's important for us to have a transient stability analysis because of those critical important significance that we said in previous slide. We want to prevent the cascade failure. We want to prevent the outage of our power sources. Okay, the massive outage of power sources, which the harshest level is going to be a blackout when all the system is collapsing. Okay. Now, that being said, if we wanted to like actually have a transient analysis, we can go fully detailed without any simplification and assumption and dive into that crazy kind of like chaos that the models and mathematics of that could bring us. Okay, because we can't use the RMS, the averaging model, the frequency-based domain kind of like analysis. So basically, we are dealing with a lot of differential equations, with a lot of like real-time models. Okay, without any simplification and assumption, that's basically, if not impossible, is very complex task to do. So we need a certain assumptions to have a base ground, and ease our way into that. Now, what are those assumptions? One is in the power system, which is a three-phase system, we assume the balance in a system. What that means, we have three phase. The balance system was that when the three phase are equal, the values are equal to each other, the power, current, voltage, whatever, okay, impedances are equal to each other. It's just the voltages and currents are 120 phase shifted with each other. Are we good on a balanced system? So instead of analyzing a three phase, I assume we already covered that in energy conversion. Okay. Instead of if we have a balanced three phase, okay, it would simplify our analysis. Instead of the three phase, we could analyze only one of the phases, and whatever result we get, we could expand it to the other two phases because they are the same but 120 phase shift. Are we good? So it's simplified a lot into our calculation. Now, the second assumption is we wanted to like simplify the generator. Okay, we can't deal with our system as a frequency domain or like reactance impedance kind of like model. Okay, but we want to like give us a break, use those models for at least our generators. So we want to like simplify the model of the generator and represent the generator with basically an internal voltage and a reactance instead of all the differential equation like a mechanical system, electrical mechanical energy conversion, all those like Faraday's law, Ohm law, KVL, KCL. Those are electrical parts. There are tons of mechanical parts kicks in into that generator, which create a massive differential equation, kind of like matrix for a generator to be analyzed in a real-time domain. Okay, to not get disturbed or like not get loaded with that kind of like massive calculations or computations, we're gonna simplify our generators with a voltage and a reactance. Also, when we talk about the transient, we already said that load flow. Let me state that this way. We already said that load flow is a steady state change, is a gradual change. Okay. Now, transient analysis is a short time frame in a very slim time frame analysis. Okay, consider that if this is our load flow, okay, with the changes happen in a like within in an hour or like a day or like if it's happened very shortly, it's gonna be a minute time scale. Okay, in transient we said we are talking about a millisecond. Okay, so it's like we are zooming in into very tiny part of this change. Correct? Now, if this is a gradual change and we are zooming massively into a very tiny part, it's not too hard to say, okay, in that time frame, load is not changing. In that very zoomed small time frame, we could consider that the load flow is static. So load is not changing during our transient analysis. Are we good? This is the third assumption. And the next one is that reduced network. We are gonna take care of like eliminating passive nodes or like, uh, some of the super nodes that we have. We wanted to like shrink our network to the critical component. Okay, so we have smaller matrix, lower analysis. Any questions so far? No? Okay. Now that we define why we need transient analysis, and we talked about the uh, assumptions that we have for transient analysis, let's build up the foundation. Like the steady state particle analysis, the transient analysis also started when we had a conventional system, when it was all rotary machine generators. Okay, so it makes sense that it is founded, or like the foundation of this transient analysis are based on rotary machine responses and their models. Okay, so we are going to talk about dynamics of a rotary machine, okay, and use that dynamic to define a transient analysis in our system. Now, in rotary machine, the transient dynamic of the system defines by Newton's second law of rotation. Okay, basically, the Newton's second law, you could search on that. Newton lets to find the derivation of a start analyzing the forces until we get the equation for how the phase angles of that rotor would swing, okay, or change. The product of that Newton's second law is that in the rotary machine, the theta of the rotor, meaning the angle of our rotor, okay, would have a second order differential equation that defines the behavior of that theta based on the mechanical torque, electrical torque, and the inertia that the system has. That J is the inertia, Tm is mechanical torque, and Te is electrical torque. Are we good so far? This is the mechanical engineering part of that model. I encourage you to look deep into that, but you don't need to understand fully what's happening over there. Is mechanical engineering or electrical? So now the parameters that we share in electrical engineering and mechanical engineering, when we talk about the rotary machine, is power. We have a mechanical power, we convert it to electrical power, or vice versa. If we have a motor, electrical power, convert it to mechanical power. Okay, so let's convert that Newton's second law rotational kind of like differential equation that we have for rotor in our rotary machine. Let's convert it to the parameters or the language that in electrical engineering we could understand or we could work with. So let's change the torques, okay, to the power. We already know that power is basically equal to torque times angular frequency, rotational speed. Okay, so using that, we could multiply the omega, the frequency, into that differential equation and change it to a new one. That j omega, we call it m. Okay, we have that second order differential over the delta, And now instead of the torques, we have mechanical power minus electrical power. Are we good so far? So this is gonna be the base differential equation that defines the behavior of our system, or in this case, the rotary machine dynamics, okay, toward any disturbance. Any question about that? No? Okay. Let's then move forward to what's going to happen. Now, in any uh, fault that would happen in our system for that rotary machine kind of like model, let me write down that this D2 is equals to PM minus PE. Okay, we wanted to like analyze this for any kind of like disturbance in power or delta. Basically, it's disturbance in power that would cause response in delta. We want to see what are going to be the responses. Okay, and in which part we are going to have a stable system based on those responses. Now, there are a series of concepts that we have to pay attention when we talk about the transient analysis. First, our general rule of power balance. We always want to have input and output equal to each other. Generating power and load demand should be equal to each other. Okay, that was a steady state. Remember that? Power flow. So power balance is the general rule that governs the behavior. We want to get that. Now, if anything happened, for example, a fault happens in electrical part, it's instantaneous. So the mechanical part would not react instantaneously. In electrical part, there is a fault going to happen. Okay, so we lose a part of our power, a part of our demand, for example, or generator, it doesn't matter. Okay, so basically a fault happens. We are in a balanced system at A when the PE, which is that curve, and PM, which is constant, are equal to each other in A, in point A. Now a fault happened, meaning our PE instantly changes. Now we have weaker electrical part. So we fell down to the new curve caused by fault. We are in this delta, so we instantly fall into the point B. Now, we said power balance governs the behavior. So the system wanted to come back to the balancing PM and PE. So it start to increasing the delta to reach the value that is closest to the PM or like equal to PM. So it goes up, for example, to the point C. Now, for example, this is a fault. After we reach that point, now we said if there is a fault, the relay would work and clear the fault out of the system. So we are in a post-fault situation. Okay. Now we have a new curve, which is stronger than the fault curve, but not necessarily as strong as previous steady state. We are in this delta. When the fault is clear, we instantly PE would change. So we are gonna be shoot to point E, the new PE. Now again, power balance is disturbed. So the system tries to keep up with the power balance and push the system to the point F to make PM and PE equal. Make sense? This is what I mean by power balance governing the behavior of the system. Now, when PM is higher than PE, like this part, like A1, okay, we call it an acceleration period because then on that part, the model wants to increase the delta, so it would reduce the difference between PM and PE. When PM is less than PE, like the blue area, A2, we call it deceleration periods. And it's because now the delta want to decrease the amount of power to meet the power balance situation. Now, we're talking about the sinusoidal system. So after 90-degree, increase in a delta is going to be the same as decrease in a delta. Is that clear? So although the delta is increasing, but the care is in decreasing behavior. Are we good on that? So that's why we call it deceleration or decelerating data. Now, in our system, when the fault happened, these changes, okay, are going to be the response, the change of the delta are going to be the response of our system to those disturbance in PE or PM. There is a delta here. We want to see what happened. Delta P, okay? We want to see what happened. System is stable. System is stable if it could handle this swing going back and forth in delta and come back to point of power balance. Now, how it would be categorized quantitatively, we are going to see that in next slides. Now, in power system, in order to incorporate that model, okay, we have to inject our values into that model. Originally, our model was m d2 delta dt square equal to Pm minus Pe. But we already know if we have a power system, Pe, based on that assumption that we have that our source is a voltage and a reactance, the generator is voltage and reactance, is going to be EV over X times sine of delta. Is the same as power flow that we have. E is internal generator, voltage is the voltage of the bus, X is the internal reactance of the generator, and sine of the delta is basically the delta that generator and the node has had with each other. Are we good? We input that model that we have for PE into our system, and now we modify that Newton's second law formula based on our own condition in power system. This is 1 over m, okay? This omega s over 2h is 1 over m. Now look at this function. We have a differential equation, second order differential equation over delta, which also have a sine of delta in it. That's what I meant by nonlinear behavior. Is that clear now? We have a constant. You know, if you integral this constant to solve this second order differential, okay, this one would become like a constant times delta. One is going to be delta, another one is going to be delta square uh, plus another constant times delta plus another constant. And this one is going to be minus sine, minus cosine, and minus sine. So it's going to be, again, and we have a minus here, is going to be a minus some alpha sine of delta. So this is going to be equal to 0. This is going to be kind of like the uh, uh, format of the solution that we might have for this equation. Clearly not linear. Okay, so that being said, we cannot solve with the previous methods or linear method. We have to come up with some values. What we're looking for is the amount of delta that guarantees the swing would stabilize. Because if the delta varies too high or too much, then we are gonna get out of that curve and the system could not come back to meet the power balance. Are we good so far? Any question? Now, what that means? What that means to have a stable system. In delta behavior, if we could have the points when delta changes the direction. So if it accelerate, after a certain point, it would deaccelerate. Okay, so you see, it goes high and then goes down, again goes high, but it still oscillates. So we have both acceleration and deacceleration, meaning in a certain point, the differential of the delta is going to be 0. If we have such a condition in the behavior of delta, then we have we have a stable system because we have both acceleration and deacceleration. If we don't have that, that means either the delta is increasing constantly or decreasing constantly. So we are not going to have a stable system because it's going to get out of hand. Make sense? This is delta behavior. Now, what would be the translation of that into the curve that we are more familiar and is based on our own parameters? If we want the delta to swing, meaning has the acceleration and deacceleration, the condition in this graph is that the area of A1 should be less or equal than area of A2. Okay, this is the condition. So you are going to point out all those dots on the curves, point A, point B, point C, point D, and point F. Then you have your A1 and A2 area. if your acceleration part is less or equal to your deceleration part, that means your delta is gonna swing and eventually get stable in a new steady state. If you want to have a visual kind of like more tangible system, consider this. This is a like a pendulum. This acceleration part is the force to that pendulum. Okay? If the force is too high, that could break the pendulum and like shoot the ball. Okay? We are not going to have a stable system. But if the force is low enough that this connection could deaccelerate eventually and handle the forces, this part, then this would swing and eventually get a stable in new position. Make sense? So this is what's going to happen. Now, all we taught was a basic transient analysis based on the model of one rotary machine. But we all know that is not going to be the case in a power system. In power system, we have a very complex grid with multiple generation and loads. Okay. Now, what's going to happen when we have multi-machine system? In multi-machine system, we have to have the same model for each of the generators. Now, why only generators? Anyone can guess why we only focusing on generator on transient analysis? The transient analysis is to understand if the system is stable when it responds to a short time disturbance. Now, in the power system, we have generation and load. Why we only have to focus on generation? We already answered that during our assumptions. Anyone can guess which of those assumptions? Static load is not changing in transient analysis. So basically, you consider the loads or not would not change it. You are static, stable. Okay, so what we are gonna focus on is the generation instead of the load and generation. So to do that, all these resources are gonna be modeled by the same model that we develop. That M second order differential of the delta equal to the mechanical power minus electrical power of that source. So we are gonna end up in a matrix of those generations. Now each of them has their own M, so Mi. Each of them has their own mechanical P, so PMI. Each of them has their own electrical P, PEI. And we know that we could use our model for PEI, which is EE admittance sine of delta theta. Are we good? Okay. Now, so far, we said, okay, we are going to have a matrix of differential equation. We are going to get it an input, which is that delta PE. And we are going to see what's going to happen to the deltas, the phase angles, that lowercase delta, okay? But we already said that, okay, that was a nonlinear equation. It's a second order differential equation that has a sign in it also. So it's a nonlinear equation. So it's not, if not impossible, it's very hard to analytically solve that equation itself. Now we are talking about the matrix of all those equations. It definitely is not possible to do that analytically. So we have to consider numerical method. What we are going to have is we are going to set up a time domain simulation method with initialized condition, which is the steady states before fault. Okay. Applying the disturbance to that steady state. So what is disturbance? We have the steady states, meaning PM is constant, PMIs are defined, and PEIs are the initial condition. Now we are gonna add to the PEI a delta based on the fault. So PEI is changing due to the disturbance in our matrix. Now what's going to happen to that delta? And what's going to happen to that delta is defined by that second order differential equation. We have to run a numerical method. Normally, they use Euler or Rangakuta method. Now I put a question mark because I wanted to ask you to look into those two methods, the Euler and Rangakuta. These are the numerical methods to solve nonlinear differential equation, or generally differential equation, just not just nonlinear equation. It's generally the differential equations that are complex or hard to solve, like in a matrix form or like tensor form. They normally use Euler or Rangakuta as an algorithm, numerical algorithm, to efficiently solve those methods. Same like, this is kind of like the same as Newton-Raphson that we use in power flow. It would help us to efficiently find the solution. Euler and Rangakuta are the same. It would help you to efficiently handle the numerical solution to get to the solution faster with low error. Are we good? Now I want you to like search on that. I want you to like search the Euler and Rangakuta method and try to get familiar with that. Rangakuta is more advanced than Euler. Euler is the basic one. Okay. If you have any question that, like, for example, you read the Euler or read the Rangakuta and you don't understand that, reach out. These are very good tools for solving numerical problems. Okay. If you get a course in math department for differential equations, most of the discussion would be around Euler and Rangakuta because they are the tools. They are the key to solve those problems. Now we have an algorithm. We have our matrix model. Okay. We have an iterative simulation to analyze the behavior of delta. Okay, based on the disturbance. Now I put a video on the slides that is actually describing an example of doing that, doing the same time domain simulation method. Are we good? Okay, that's it for
Enjoy
today.
the rest you
We are already covering the transient analysis of the power system. Next session, I'm going to introduce what's happened if we have IVR in it, because so far we didn't talk about inverters. That's a general conventional method of transient analysis based on the swing equation of a synchronous machine or rotary machine generally. Okay, we already seen that that's not gonna, the inverter is gonna introduce a buckload of complexity into that analysis. Okay, we are going to talk about that in next session. Now, I also put lecture notes. I will post more videos and more files uh, for you guys to get deeper into how you can run a transient analysis on a power system. Okay, but I also want you to search on that. Okay, now this is one thing. Simulink has the ability to have a transient power analysis. Okay, but later on we are gonna see that the best option, although uh, MATLAB Simulink is kind of like could handle the basics, okay, but is not accurate enough when we talk about the inverters. So I encourage you to start thinking about having a M file for the algorithm of time domain solution uh, methods, okay, and implementing either like Euler, which is the basic one, or Rangakuta, which is the advanced one, okay, in order to develop your iterative algorithm to solve for delta. Is that clear what I mean?
So you want us to make an end file?
I suggest you to do that.
Okay.
Simulink has the transient analysis, okay? But honestly, uh, it's not accurate enough. When we enter the inverters, it is based on some assumption that will not give us the true answers, okay? If you have an M file, you have flexibility of changing parameters. Are we good? Okay. Any question? No, guys in the Zoom, any question? No? Okay. So that's it for today. I hope you will have a great rest of the day. Thank you.